Hello everyone, my name is Yihan Rong. Today we are going to share about our machine learning project on the analysis and calibration of neural networks for skin cancer diagnosis. There are 4 members in our team: Hao Guangyuan, Yihan Rong, Tian Haisheng, and Fang Xianghong. This is the contents of our presentation. We will introduce a skin cancer classification task, and then we will talk about what is calibration and miscalibration for deep learning models. We will go through some typical calibration methods and show you our experiment results. Skin cancers are cancers that arise from the skin. It is the most widespread form of cancers, globally accounting for at least 40% of cancer cases. To diagnose skin cancers as early as possible, the doctors are required to classify different types of malignant skin cancers and pigmented skin lesions in the clinics based on the visual features. The pigmented skin lesion images may be disturbing to some audience. So here I go. As you can see, different kinds of skin disease have different appearance. The experienced doctors can tell the difference between different kinds of skin disease with naked eyes. With the aggressive development of image classification methods with deep learning models, we can use a powerful models to classify these disease images. However, there is a big challenge when we try to apply the deep learning models to the skin disease image classification problem. The challenge is, can we rely on the confidence values produced by the Softmax layer of the deep learning models? If not, the model is dangerous because we don't know when it is correct and when it is wrong. This is an example. The first row is the prediction. The first column is a prediction of the deep learning model after Softmax layer. And the second column is a true likelihood of this class. Here, the model is quite sure about the images shows disease A, but the true likelihood is just 55%, and it needs human expert to examine it again. So if the doctor here choose to believe the model 100%, and the patient will be misdiagnosed. So here comes the motivation of this project. First, we want to find out if these confidence values are accurate or not. If they are not accurate, how can we improve it? The answer of the first question is no. The deep learning models tend to be overconfident. To show how reliable the confidence values are, we can use 2 diagrams. The first diagram is a confidence histogram. The x-axis is the confidence level, and the y-axis is the number of samples. As you can see here, the average of confidence is much higher than the accuracy, and the model show very high confidence on many samples while they are not accurate. And the second diagram is called reliability histogram. The x-axis is different confidence level, and the y-axis is accuracy. As you can see here, for most of the bins, the blue one, the accuracy of the model is much lower than the confidence of the model. So it means that the model is quite well overconfident. Okay, so and for the net, it is relatively well calibrated. The prediction, the confidence prediction match the accuracy very well. So what is a perfect calibration? It means the confidence of the model is equal to its accuracy. In practice, we divide them into different bins and calculate this value. So to measure how well the model is calibrated, other than these 2 diagrams, we can use a measure called expected calibration error, ECE. The calculation ECE can be visualized here. We first divide the confidence into different different bins. For example, we take this one as a sample, P bigger or equal to 40% and smaller than 60%. It is average confidence of these 2 samples are 55%, and the accuracy of this model is 50%. So after we minus them together, we have the 5%. And because we have 2 samples here, so we will have a gap equal to 2 times 5%. And then we do normalization over all the bins, and then we can have the expected calibration error, ECE. Okay, now let me introduce my teammate Hao Guangyuan to introduce to talk about the reasons for the miscalibration and calibration methods that we can use to avoid this phenomenon. Thank you.
So why do we have such serious miscalibration on the deep learning models? I will introduce miscalibration reasons and the calibration methods as following. There are several deep learning techniques that can improve accuracy. We list them in the figure. For example, different models and wider models using Bayesian normalization, using small weight decay, and blue color indicates error, and red color means ECE score. As you can see, all techniques can improve the accuracy, but also improve the ECE score, meaning they are harmful to the calibration. The negative logly likelihood refers as the cross entropy loss, which also causes miscalibration. We observe a disconnect between error and accuracy in the training curve. Figure 3 shows text error and error on CIFAR 100. Both both error and error immediately dropped at epoch 250 when the learning rate is dropped. However, error overfits during the rest of training, meaning error is surprisingly increased. Overfitting to the error is benefit to classification accuracy on the CIFAR 100. Text error drops 2% in this region. This phenomenon gives a concrete explanation of miscalibration. Overfitting to error is harmful to the calibration. We then use 5 kinds of calibration methods to calibrate our models in experiments. There are 2 methods based on bins and 3 scaling methods. All methods are post-processing after models are trained. Simply speaking, HKUST bins is to output a calibrated probability CIM for each bin with bin and boundaries AM fixed. Specifically, all predicted p-hat are divided into M bins, where, for example, the bin 6 is defined by the interval A6 to the A7. The bin boundaries are chosen to be equal length intervals. Secondly, each bin is assigned a calibrated score theta m, meaning if p-hat is assigned to the bin 6, then the calibrated prediction will be the theta m, theta 6. The predictions theta m are chosen by minimize this loss. Isotonic regression can be treated as the generalized of histogram bins. It's easy to find that in the histogram bins, we can just need to optimize the predictions theta, but in the isotonic regressions, we jointly optimize the prediction theta and boundary AM, meaning that the boundary AM are not fixed. In this method temporary scaling, we get calibrated prediction by divided all logarithm z with a same value t. In order to estimate t, we optimize t on the validation side by fixing all the parameters of pre-trained classification models. When error is reduced, we will get well-calibrated predictions. There is another benefit. The accuracy of models will not change. This is because all logarithm are divided by a same t, so that the relative size of logarithm will not change. We will introduce the rest of 2 methods together, matrix and vector scaling. Different from temperature scaling, we use a matrix W and a vector B to transform the old logits ZI into new logits. Similarly, we estimate W and B by reducing an error on validation site. Notice that we define that in vector scaling. W is a diagonal matrix. Let's welcome the next speaker, Shen Tian, to talk about results and conclusion.
Okay, I will show the last part, result and the conclusion. In the experiment part, we apply 5 calibration techniques to image classification neural networks. Specifically, we used 2 datasets, MNIST and HAM 10,000. And the 5 methods include histogram binning, isotonic regression, temperature scaling, vector scaling, and the matrix scaling. And we use 2 different data sets here. We aim to verify the effectiveness of those 5 calibration methods in MNIST dataset. For the second task of HAM 10,000 datasets, the models are required to classify 7 different types of skin disease. We show the details of this dataset in this page, as you can see. To commence with, we apply 5 calibration techniques to image classification tasks in MNIST datasets. As mentioned before, expected calibration error and reliability diagram are introduced to measure and visualize calibration. ECE is the key metric that can offer us the value of how miscalibrated the neural network is. As for reliability diagram, what I would like to see is that it should be an identity function that shows that our confidence score reflects the accuracy of that things. Look at the ECE below. Most calibration methods could improve the confidence gap since those methods can reduce the value of ECE. Please look at the right red circle. Those red rectangles refers to the confidence gap. The one exception is the matrix scaling method, which abnormally increased the ECE. But we observe that all ECEs are typically below 1%, and the MNIST datasets have very low error. Referring to the top row confidence histogram in figure 3, the average confidence is very close to the average accuracy. Hence, there are not much room for decreasing the ECE in this dataset. To conclude, most calibration methods still improve the calibration, and the isotonic regression outperforms the other methods. Okay, in our second task, we use HAM 10,000 datasets. Look at the ECE below. All the calibration methods show the improvement of ECE. It's worth noting that matrix scaling outperforms all other methods on this task, although it performs poorly on MNIST. Those 3 scaling methods performs in the same level actually. In the light of the top row confidence histogram in this figure, it is obvious that to be confident since the average confidence is larger than the average accuracy. Simultaneously, the reliability diagram also shows the OV confidence. In fact, the whole beans in the reliability diagram should lie on the diagonal in the perfect situation. Obviously, those 3 scaling methods could produce much better confidence estimate compared to the other 2 methods. In general, isotonic regression outperforms the histogram binning on both datasets. Okay, finally, let's make a brief summary. 5 calibration methods applied to network calibration on MNIST and HAM and 10,000 datasets, and show their effectiveness actually. Histogram binning and isotonic regression outperforms the other 3 scaling methods on MNIST. However, the 3 scaling methods could produce much better confidence estimate on HAM 10,000 datasets. That's all. Thank you.